So hello, my name's Evan. I'm very happy to be here. I work at Celestia, the first modular blockchain network. Here's my Twitter and GitHub. If you have any questions during either this talk or about Celestia in general, you can go ahead and ping me whenever you feel like it. I'll also be here all week. So I work on Celestia Core and Celestia App. Celestia Core is our fork of Tendermint, and then Celestia App is our state machine. So effectively, I work mostly on the blockchain part. So the title of this talk is Celestiums, Scaling Ethereum L2s by Using Celestia for Data Availability. So the main problem is with rollup transactions is like they still get pretty expensive, and that cost has to go somewhere. Someone has to pay for it. Maybe you have some very ambitious VCs that pay for these things. But most of the time, we have to pass that cost on to our users, which is not very desirable. You can kind of see here, I think the light blue is Arbitrum. And this wasn't even that long ago. So it's not like a raging bull market. And it was I don't know, 70 or 80K a day at peak. It's that can get pretty expensive. So what do you do if, it's why is this so expensive? So there's a reason why the Ethereum 2 roadmap isn't just increasing call data. It's because that's not scalable. It's all the full nodes in the network have to download that data. And then along with downloading all that data, you have to run the entire rest of the state machine, right? You have a lot of smart contracts that are on the L1. And not only that, but the call data is priced in the same way that the rest of the contracts are. It's just priced in gas. So you have to compete against everyone else for whether it's $1 million arbitrage or someone's minting some NFTs. It's you have to compete against that just for your call data for your rollup. And again, that can get expensive. So it would be nice if we had more options. It's what can you do if you have a project that isn't, or you want to have a project that you want to have some really good security, you want to be involved with Ethereum, but you don't have high profit transactions. It's not necessarily that the transactions aren't valuable, it's just that they don't have a lot of profit. So people have to pay for them. So what do you do when you have a lot of transactions that aren't profitable? Okay, so there is another option that some people use, and it's called a data availability committee. No joke, it's just a multi-sig, and it just tells the contracts, it's yes, this data is available. That's it. It's a multi-sig. These are used all over the place. We know they're not secure, especially compared to the security of a rollup. So with the security of the rollup, effectively, if you have your contracts right, organized correctly, then you effectively inherit the entire security from the L1, which is amazing. That's an amazing scalability property, because now the L1 doesn't have to have transactions be executed on it. But it can be expensive. Using a rollup on Ethereum, programming a rollup on Ethereum is actually really easy. It has out-of-the-box solution for call data, so it's really simple to implement. A data availability committee, on the other hand, you have to build yourself. It's there's not that many good open source, battle-tested implementations of these things. So that's a thing that you have to audit, and you have to make sure that there's no bugs in it. It's what if there's a bug that erases everything for all the nodes? It's well, that's a pretty big deal. And then, so it's difficult to implement. It is cheaper, but it's also incredibly insecure. So it's just not a good option. So enter Celestiums. That's what we're trying to do at Celestia. That's where you take the block data, which is a significant chunk of the cost of your rollup, right? The call data that we were talking about earlier. And effectively, you just post that on Celestia. And then we have a way to prove that that data was posted on Celestia on Ethereum. And this essentially gives you the security that your call data has the security of Celestia. You use Ethereum for settlement and consensus. You get a significantly cheaper price because, again, your call data is going on Celestia. And importantly, from an engineering perspective, it's built for you. You don't have to implement these things. These things are like already out of the box. You just post data on Celestia, already done for you. The contracts that you use, already done for you. It's like a single method. And we'll cover these things in depth a little bit more later. But here's like a nice little graph. You can kind of see like what we're aiming for. So Celestiums, no, they're not as secure as a rollup. Like, but at the same time, they do have like a really good trade-off space, like a really, really good happy medium. And again, we'll cover a little bit more of that later, like why Celestiums are more secure and why data availability committees are not. Oh, but I highly encourage you to go check out our blog in general, but we have a great specific blog post. Shout out to Aditi and John who cover like more in depth this specific concept and go into like a deeper cost analysis. So this is kind of the whole idea of Celestiums, what we were talking about, is you publish your data on Celestia, you publish the proofs for your rollup on Ethereum. It's pretty simple. We have a bridge right here that is a light client relay that we'll get to talk about in a little bit. And you prove that your data was posted to Celestia on Ethereum. That's basically all you have to do. The implementation is probably, well, it is a little bit different for an optimistic rollup or ZK rollup or whatever your use case is, but again, it's still pretty easy to implement. So why use Celestia for data availability in the first place? And because like if Celestia isn't very good at data availability, then it's not really going to help you that much. Or if a lot of people use it, then effectively you'll just run into the same issues that you were having on Ethereum. So we want to use Celestia mainly because it's really scalable. And this is like one of my favorite reasons why Celestia is so scalable is because it doesn't have an execution environment. So that doesn't really sound like a feature. It's like, no, that sounds like that's not a feature. But in fact, the design of it is so elegant that removing things actually provides you more. It provides you more scalability, more data throughput, and you just have to get a little clever in the design. So this no execution also enables modularity. So we have like a normal monolithic chain. You have your execution, your settlement, your consensus, and your data availability. Everything happens on one chain. This is just every normal blockchain that exists today. And then enter Celestia. It doesn't have an execution environment. Instead, it only does consensus and data availability. It focuses just on those things. And then it lets the rollup decide what it wants to do for settlement or for execution. So going back to that there's no execution environment, what's like the main bottleneck for every single blockchain? It's the state database. It's like, it costs a lot of money to run. And this is why like BSC, we don't consider BSC decentralized. It's like one, it has a few validators, but also you can't really run a full node yourself. It costs too much money. So this is like the main bottleneck. So for a blockchain, if you're just trying to build like the blockchain that can hold the most data, it's like one really good way to do that is to get rid of the execution environment. And then now you can essentially, all the money that you were spending on that state machine, you can spend on bandwidth instead. Ah, yes, and if you don't have an execution layer, you're obviously the data that you're paying to store isn't competing for L1 transactions that are very high profit. Oh yeah, and this is just to show how small our state machine is. This is the additional state machine, so it's not the full one. Like we have to run some proof of stake logic and a few other things. But besides that, it's basically just Tendermint, and then you can see this one little function up here that says consume gas for the size of the message. That's it. That's it. That's kind of crazy. That's like the most of the state machine for Celestia, and that is one big reason for why we are so scalable. Now, the other reasons is actually has to do with trust minimization. So like you can't really become a modular blockchain. You can't really focus on data availability and consensus and let other people focus on what they're good at if you don't do it in a trust minimized way, right? So ideally you run a light client and you have so much confidence in the rest of the network that you don't have to run a full node. Because otherwise that's not really scaling. If you also have to run a full node along with your rollup full node to have the full security of the network, then that's not really scaling. So Celestia has been designed around the fact to have something that's never been done before, and that's trust minimized light clients. So the light clients themselves, we organize the block data into this thing that's a square. It's called a two-dimensional Reed-Solomon Merkle tree. And we effectively have the light clients sample it. And now there's a lot better explanations, and just for time-wise, I'm not going to go into like the little details on how this gets done. But again, if you do have more questions, there's plenty of other talks on YouTube, or you can go to our blog. But effectively, the light clients, when they sample, they basically convince themselves that the block data is available. And not only that, but they listen for different types of fraud proofs. So if you're listening for fraud proofs and you know that the data is available, then effectively you have the same security as a full node, which is really crazy. It's like you only have to run a light client plus sampling, plus listening for fraud proofs, which isn't very heavy, but then you have the same security, or essentially the same security as a full node. That's crazy. And it's a very, very, very powerful scaling primitive. And we'll dig into this in the next slide or two, but you also, as a light client, you contribute to the security of the network. So this is kind of another amazing thing with Celestia and why it's such a good data availability layer. So, so the first point here is the data downloaded by light clients increases only by a square root. So like the amount of data that you have to download as a light client compared to the actual size of the block has this great scaling primitive where, again, like you only have to download a very small portion of the actual block. And then more light clients means that larger blocks are more secure, because one of the security aspects that could happen is like all the validators could collude and they could stop serving all the data. And if you're a light client, you've already sampled, you've already convinced yourself that the data is available, but then the validators don't serve it when you ask for it again. So you have to basically have a way around that. And the way around that is you just ask other light clients for the data that they sampled, and then you can reconstruct the entire block. You use the erasure codes that we were talking about earlier in the 2D square. And so the more light clients that you have, the larger block that you can have in a secure way. So again, for trust minimization, if you are using a Celestium, you can also sample the data yourself. Now, it's not as good as a normal rollup or the smart contracts being able to sample. They obviously can't sample, but you can at least sample and know for a fact that the data is available. Or if you just wanted to download your data directly, this is also a convenient way to just download your rollup's block data if you wanted to do that, or not your rollup, your L2, your Celestium data. And just some random other cool things about Celestia is we talked about we're the first modular blockchain. Actually, we weren't made to post data on Ethereum. We were made for something that's called like sovereign rollups. So this is, it's basically just a normal, it gets the benefits of being a normal blockchain, right? You can hard fork, you're sovereign, you have full control over that part of the blockchain, but then you also get the scalability benefits of a rollup. So there's other posts on our blog, and I would really encourage you to dig up those. They're like my favorite thing in the world. Anyway, it's also very easy to use. You don't need to spin up a validator set or anything like that. You just use a data API. Same thing with the rollup or your Celestium is you basically just use Celestia as an API to post your data and to fetch your data. Oh yeah, and then well, also we also have Mustafa Al-Bassam. He's our CEO. I'll just leave it at that. You should go search him. So yeah, so this is getting us back to sort of like the first point, is how do we actually prove that any data was posted to Celestia via the EVM? So if we go back to here, we have you publish your transaction data on Celestia, you publish your proofs, but this thing down here, the relay validator signatures and Merkle root, we still haven't talked about that. And that is called the quantum gravity bridge. So this is a light client relay. It's a light client, meaning that you still have to trust the validator set. But you don't verify the state, but you do verify the commit. So you have to trust that 2/3 of the validator set effectively don't collude. That's the trust assumption that you're making. But so this is equivalent to kind of IBC. So if anyone's familiar with IBC, the QGB is to a data availability committee, as IBC is to a multi-sig bridge. If you want to compare the two, IBC, I have like a green check mark and sparkles next to it. It's very nice. It's been up for, oh boy, I don't know, like at least 18 months. It transfers billions of dollars every month. It's very secure. As opposed to a multi-sig bridge, it loses billions per year. It helps fund North Korea. It's permissioned as opposed to IBC and the QGB, which are permissionless. The multi-sig bridge is almost always the weakest link of security between whatever you're using a multi-sig for. So again, you want to avoid them. IBC and the QGB are crypto-economically secure. So you can slash people. If data isn't available on Celestia, then that block is invalid. And effectively, we have to go to social consensus because the chain halts. And we have to slash the validators and start the chain from scratch. Or not from scratch, but we just have to hard fork and continue on from there. So the IBC and the QGB are crypto-economically secure. The multi-sig bridge and the data availability committee are not. They're basically just reputation-based. That's great. That's not secure. We all know what happens. Ronin, Harmony, probably another one since then. But yeah, I cover these things again, but they're identical to what they were before. Okay, so the QGB has a lot of optimizations. We batch a lot of things. So we batch like our data commitments and our validator set updates so that effectively the relayer, the thing that bridges the data from, or bridges the commitments from Celestia to an EVM chain, it really doesn't use that much gas. Another great thing is that it only requires a single relayer to be live. This relayer is completely trust minimized. You don't have to trust it at all, so you only really need one, which is kind of really nice. All the block data on Celestia is committed to. So the QGB transfers all of the block data, which again is really nice. This kind of means like if your rollup, like in this specific scenario, if you have a optimistic rollup that is using Celestia for data availability, and then, or a Celestium that is using Celestia for data availability, and you effectively don't have to pay more, like you have to pay Celestia more, but your gas usage on Ethereum doesn't increase at all. So again, it's a really, really good scalability primitive. And then we also, the QGB is a one-to-many design. So if you post data on Celestia, then any EVM chain can effectively run the QGB, and you just need one relayer to relay to each of them, and that's it. Okay, so we can cover some slides. I'm kind of rushing, I'm sorry, I'm running out of time. So I won't cover like details into slashing, but effectively, if the chain goes down or if the QGB goes down, we can slash. Same thing with incorrect signatures or equivocation. I wanted to go over very quickly over how the QGB is actually used. So this is the single smart contract method that you would use. And effectively, you're just verify attestation. You want to prove that some data was included into the commitment. and that's basically it. That's literally all you have to do for your contracts to use the QGB. And posting data, I don't think I updated that image, but yeah, I forgot to update the image. But effectively, there was some other like light client code. It's effectively a REST endpoint. It's like you submit data via REST endpoint. Done. Okay, so very quickly for the conclusions, Celestia is a really, really scalable data availability layer. And now we can finally have like another option, just something decent besides a data availability committee, which are absolutely terrible. But also if you can't afford the full security of Ethereum with a rollup. And it's coming to a testnet near you. We have like working versions of these things. Pretty soon we'll update our testnet. So we have a testnet going on right now called Mamaki, and we'll update it to be able to run the QGB. And then we will run the QGB on some Ethereum testnet, and we'll be able to play with it. Ah, yes, we're hiring. Go check out our website. I think we're just celestia.org. And that's it. Questions? We only have 2 minutes for questions. I'm super sorry.
Wait, 1 second. Excuse me.
I was wondering how is it proven that data isn't available on Celestia? Like, how does that happen?
Well, if you're a light client and you're sampling for data availability, then effectively one of the samples that you ask for won't be returned. And then that's good enough for you to say that the data isn't available.
Okay, but
Pretty sure on that.
You also said the chain will halt in that case?
Light clients halt.
Oh, the light.
So yeah, the light clients halt. So all honest nodes in the network will halt. If something bad happens, all honest nodes halt, and the validators, just like any chain, can like if over 2/3, technically they can produce blocks, but all the rest of the nodes will halt, and then we'll just hard fork at that point. I will definitely be one of the ones hard forking at that point.
Yeah.
So, but we'll slash them and then move on with our lives.
Oh, okay.
Yeah.
Okay.
One of the
Thank you.
great things about Tendermint is it's very like fully accountable. So it's very easy to trace these things, and like we even like run through like test runs of hard forking. Like there's a lot of other things. But anyway, next, do we have any more questions?
Okay, so let's say that we have a ZK rollup, and of course we need to prove the data that it's behind the transition. So we have a hash representing this data. How much would it cost to prove that this hash it's included on Celestia, as in all the data that it's on the block or transaction or batch or whatever?
With the ZK rollup, it's definitely doable, but the main cost is from the prover. So you have to prove, we use SHA-256 currently. So, and we don't plan on changing that. So you have to effectively like prove the Merkle root of all your data to that hash using SHA-256. So that's the expensive part. Now we do have some interesting solutions to that. And, but I don't think we have time to talk about that now. Find me sometime.
Okay.
Timeout. All right. Well, thank you all. Sorry I didn't have enough time to